Hello, gentlemen. Welcome back. Hope everybody finished up week one in fine fashion and completed the problem set, and it went well. Again, if you have any questions on that and you want to review any of those problems, make sure that you let me know so that we can make sure that you have all that material down pat. But let's move on. We finished talking about quadratics at the end of last week, and today we're going to start looking at polynomials of higher degree. Okay. First, I want to talk about something called continuity. And we talk about a function being continuous on an interval. We have to meet a couple criteria here. First, the function has to be defined on each point in the interval. Okay. And the second is the graph doesn't have any holes or gaps or breaks in it. All right. And so something like this would not be continuous because we have a break in here. Right in this area right here, okay, we have a gap. All right, so we're not going to be continuous at all in that situation. Okay, and so if something is continuous, it's going to be a smooth curve and it's going to have no gaps or breaks in it. All right. Polynomials are continuous for all real numbers. All right, and I want to make a note of this rounded smooth curves. All right, right here. Okay, polynomials don't have any holes. They're continuous for all real numbers, and there's no sharp turns. Here's an example right here of a polynomial. This is of degree 4. Remember, we talked about degree last week. And I want you to note that the rounded, smooth curves here. Okay? I'm not seeing anything like this. So if I had a graph like this, like the absolute value function, that's not what we're going to have for polynomials. You're not going to have any transitions like that right there. Okay? Function is going to be defined for all real numbers. There's going to be no gaps or no holes in this graph at all. Okay, for any polynomial. Now, if we start to look at, the behavior of certain types of functions, we'll see we're going to look at the end behavior, the beginning behavior, but it's important to understand about monomial functions. They're just in the form of x to the n. There's no other stuff here. An example would be something like, f of x equals x to the 5th. That's a monomial right there. Okay? There's only one term in it. All right? And we want to know what it looks like if n is even. Let's look at n is even first. Okay? Any even formula, any even n here is going to give me a shape sort of like a parabola, but the steepness is going to depend upon the coefficient. Okay? An x to the 4th is going to grow much more quickly than an x to the squared. Note though this area right in here before we get to 1. This is going to be 1 where I'm going to intersect. The x squared actually is above the lower degree graph will be above the higher degree graph between 0 and 1. But after that, the higher degree graph will start to grow much more quickly than the lower degree one. Okay? So all x even functions are either going to always end up going off to infinity or negative infinity, as we'll see in a minute. Okay. The steeper the value of n, the flatter the graph. This is what I was talking about between 0 and 1 here. I've sort of magnified that part for you. This black curve is the x squared term. The red is the x to the 4th. And before I get to 1, this number here, this graph is going to be up on top of the x to the 4th. And then they're going to switch locations there once we get to 1. Okay? Hopefully that makes some sense to you. Let's look at if it's an odd function. It's going to sort of look like a cubic function. And again, the steepness is all going to depend upon the degree of the polynomial. Okay? 5th is going to grow a lot faster than a 3rd. And that's why it's going to be on top. Again, we're going to have that situation between 0 and 1. Same type of idea that we had before, where the lower degree will be on top of the higher degree just between those two numbers. And you can think about that as, say, if I had a half times a half times a half for a 3rd, if I had a half times a half times a half, I get an 1/8. Okay, but if I had it 5 times like this, I'm I'm going to get a 32nd, okay, and so I'm getting smaller and smaller, all right, and that's why you're seeing it below, right there would be a half, below the x to the fifth is below the x to the cube, okay. Leading coefficient test, this is going to tell us the behavior of the graph, what it's going to do as x gets larger and x goes off to positive infinity and negative infinity. If a sum n is greater than 0, again, this is n is leading, so this is n is even, so this is x squared, x to the fourth, x to the sixth, something of that nature. If a sum n is greater than 0, as x gets large, the function value is going to go off to infinity. As x goes to negative infinity, the function is still going to go off to infinity because any number to an even power is always going to become positive. Okay? And then if a is negative, okay, less than 0, the graph is just going to get flipped, and we're going to go off to negative infinity in both directions. Okay, because that would be something like, you know, if I had like negative x to the sixth, this term is always positive. This makes it negative, so that we're going to go off to negative infinity in both directions. Okay. If n is odd, we're going to get something like that. If a sum n is greater than 0, as x goes to infinity, the function is going to grow without bound to infinity. When x heads to negative infinity, the function is going to go to negative infinity. And that's primarily because if I have something like f of x equals x cubed, if I cube a negative number, it's still negative. So as I go off in this direction, negative 1,000, it's still going to give me a negative value. And so we're going to go off to negative infinity there. If a sum n is less than 0, they're just going to flip-flop positions. So if I had, you know, if I look at this example again, and then if I put negative out front here, when I put in, say, negative 1,000 cubed here, this number is still going to be negative, so I'm going to have a negative times negative 1, we'll say, times 1,000 cubed. Those two will cancel and become positive 1,000 cubed. Okay, so again, understand that if when you cube a negative number, you still get a negative number back. Here's some practice. This is just an introduction to section 2.2. There'll be another video on it. I want you to pay attention to this leading coefficient test. Here are some problems here. Again, if you have any questions, you need to email me. Basically, the things that we talked about in this video is continuity. You know, what makes a function continuous. Basically, all the values in for all real numbers for polynomial, the function is defined. There's smooth curve. There's no holes or gaps. There's no sharp turns. We looked at the leading coefficient test, which is going to tell me the end behavior of what's going to happen with those curves. And we looked a little bit at monomial functions. Okay, so there's a quick introduction to section 2.2. There'll be another video on it and some more practice problems. Okay, gentlemen, have a good day.